So the broad idea is I wanted to start off from last time. We were doing what do we call it properly? So last time, so what we tried to understand was that if you have x and y are two continuous random variables, they both have PDFs. And then, so I discussed that we may have a joint density function, that is fxy is a function from R2 to the negative positive half plane. Fxy is non-negative, first of all. And then fxy is again piecewise continuous. And the double integral of f over the two regions of x and y is equal to 1. That's the joint density function. And then what you would call this the joint PDF, in the sense that the chance that x and y belong to some event A is going to be given by the integral of A fxy dx. And we also understood this joint distribution function. Which was like f at x comma y was the same as the chance that x is less than or equal to x and y is less than or equal to y. So maybe I use the words a and b here. So f of a comma b is x less than or equal to a and y less than or equal to b, and that's just the integral from marginal to a marginal to b of f of x y. Here I put dy dx, so I'll put y first. So the integrals over f give you the probabilities of x, and in turn the distribution function is given by this joint. And we also saw in one example that that if I differentiate, if I want to find the density of x, f sub x at a, that was the same as differentiating f as a function. And similarly, f sub y at b was dou by dou b of f at eta. That's one. These are called the marginal densities. I'll explain this today. And we have done this through two examples. One example was the following. So we have done this through two examples. So two examples. One example was the following, that I said that let D be a subset of R2 with finite area. And this example was fxy was given by 1 over the area of the set D if x and y were in D, and there was 0 otherwise. And the other example that I had stated was, this one example was that fxy was equal to, I think I called it x plus y. Let's check that. Is x plus y when 0 is less than x less than 1, 0 less than y less than 1, and 0 otherwise. So these are two examples that we have done so far in combination. So I'd like you to keep this in mind. This was a example, let's say, we call it as this is 5.4.3, and this was 5.4.5. And we had computed some probabilities with regard to these figures. So in this thing, I had shown you that this was same as thinking of x and y was uniform, was choosing a point uniformly in the region D, and this was not like uniform, something else. That's where we were last time. So we'll just quickly recap a little bit so you can see the whole recap. So today, I just want to start off with a very simple idea for of marginal density, which we will develop in a second. So let's go there. Oh. So here's the first definition. Let me start this as so here's a section on marginal density 5.4.1. So here, x and y are random variables that and have a joint probability density function. Density function f from R2 to R0. That's given to you. Then the first thing you observe is that we observed last time, was also the example was that the chance that x is less than or equal to x alone, so you could think of it as the chance that x is less than or equal to x, x, and y being anywhere. So y is anywhere. This is these two events are this event has probability 1, so I can intersect it with x. And that we knew from definition was minus infinity to x, and the inside I'll write as minus infinity to y, infinity of f at x comma y dy dx. So dy dx. That's it. Now if you observe, just think a little bit, you observe, so suppose I call the inside part as g of x. Okay, this is g of x. Okay. So that is, I think of it as g of x. So that means g is a function from R to R, R to 0 infinity, given by g of x is the integral of infinity to infinity. Let me write that in red again. So it's here. So let me just copy this. Duplicate it and bring it down here. This way. So let me erase this. It's already blue. So it's f at the point x comma y dx dy. So I integrate out the y variable in f. Now, suppose I give you this function, right? So this is like this. So what do you notice? So this implies that the chance that x less than or equal to x is given by minus infinity to x g of x, so I should say again, I'm using this xn as an integrand and the variable. Let me go and change that. So we call it x less than or equal to a, x less than or equal to a here, and is okay. And g of x remains the same. And then I come here and I say, okay, fine. So x less than or equal to a is a g of x dx. So now, if you look at it now, look at one variable review, you immediately see that, oh wow, this is x is given by the integral. This implies that the density function of x at the point A is just the derivative of this integrand, which by the fundamental theorem of calculus is just g of it. So this requires a certain assumption that g is continuous. Otherwise, this is true whenever g is continuous, at all points of g is continuous. So now this is a kind of an interesting idea. That means we have derived the joint density function is just going to be equal to minus infinity to infinity Let me write this in red again. Minus infinity, always copy this. It's minus infinity of the joint density function at the point. So all I do is I just integrate out. There's too many colors here. Let me just erase this color. So here the idea is that is f at the point a comma y. So if I integrate out the joint density for a fixed value of a in the y variable, then I get the marginal density of x. And similarly, one can show f sub y at a point b is just, let's say, the integral from minus infinity of at the point x, and then I integrate out dx. So this is just one f at the point x comma b of dx. This is true for all a and r. This is true for all a. So now this is something, it's quite interesting. So from the joint density, you can get the two marginal densities. So these are called the marginal densities. These are called. So once I have x and y dependent in terms of f, these two things are called marginal densities. So let me just quickly recap this calculation a little bit so that you all can see in one page. So the idea is that that if x and y are two random variables that are given by a joint density function, then you can get the individual density by integrating out the other variable. Sort of makes sense. So here, let me just write down the topics I'm going to cover in this area. So this is like let's say. So first is so this is marginal density. I'd like to understand that. Then let's try to understand. That means I can understand the individual ones given the joint one. That's what marginal is. Right? Then I understand what independence is now. Next, let me do independence next. So what is independence? Independence means so let's do 5.4.2. So independence. So what does independence means? Independence means that so if I have two random variables x and y are two random variables, we already said, we already recall that. So let's recall that they are independent if what all happens if the ideal way is that if x is in A and y is in B is the same as the chance that x is in A and the chance that y is in B, right? This is the basic definition we had before. But that's we remember last time we said that this was equivalent to just checking if the distribution function, that is y less than equal to x, y less than equal to y, split up as the probability of x less than equal to x times y less than equal to y. So it's enough to check this equation. But that is the same as saying that the joint distribution function fxy is the same as the individual ones multiplied together. So this is something that we have realized, right? This is the definition. So now you observe that, okay, so if they're independent, this is true for all x and y. Right? This is true for all x and y. So if the joint distribution function splits across, then you have the idea that random variables. But let's just try and see how does this compare to the density function, right? So now, so this one way is clear now. So now suppose this splits up. So one way is clear. So this implies if x and y are independent, this is like, let's call this a star or dagger, let's say dagger. Sorry. If x and y are independent, then what does this dagger imply? Dagger implies, so if I can allow myself to differentiate in each variable, what will I get? On the left hand side, I'll just get the density function of x and y, the joint density. On the right hand side, this only depends on x and this only depends on y. So I just get f sub x at x times f sub y at y. This should be true for all x and y. Right. So let's assume the fact that f, under the assumption that of f being continuous, f sub x and f continuous. If they're not continuous everywhere, then you need to verify that all continuity points. But broadly, the joint density function will split up as a product of two density functions. That's an important factor. Now, let's converse. Let's do the reverse converse. Suppose I give you the reverse. Suppose, let's do the converse. Let me write it in green so that's clear. So what about the converse? Conversely, let's say let x have PDF f sub x, y have PDF f sub y, right? And suppose the joint density function f comma s is given by f sub x times f sub y is joint density. The joint density is given to be the product of the two marginal densities. Okay, suppose this is good. Then you can verify the following idea, right? So then you can easily verify, let's say you take the chance that x is in A and y is in B. Right? Let's do it generally. So that's the same as integral over the set B, let's say, over the set A of f of x, y, dx. That's by definition. But now I know my f splits up into two parts, right? Let's split up into f sub x at x times f sub y at y. Right? That's what f looks like. And I have a dy, and I have an integral over b, and I have a dx integral over a. Okay. Now that's the same as, if you write it properly, let me get the black part again. That's the same, let's come down, that's the same as, I can write the integral separately now, the green part separately. So we have the green part, same as integral over b, since everything is non-negative, so integral over b is in blue, I guess. So it's a y variable, f sub y at y dy is the y, we'll put this a little bit further away. And I have an integral over the y variable, the x variable. So f sub x. Now this we know is the same as the chance that x is in A and y is in B. Right? So this equality is true for all events A and B. So it's true for all events A and B. So this implies that x and y are indeed independent. So now this is an interesting fact we've shown, that independence means that the joint density splits up as a product. It's a kind of crucial fact. So that means, so what we've shown in this argument is that if x and y are independent, it's equal to checking that the joint density splits up a little bit. So let me write that down. So this is a remark. Go back up. So So what we have shown is that on the one hand, x and y are independent. Let's say continuous random variables. Right? That's equivalent to the fact that the joint density function f of x comma y. So let's say that's equal to the fact that the joint density is equal to product of the marginals. Right? In marginal of x, marginal density of x times the marginal density of y. Joint density of x comma y is the same as the product of the two models. That's what this calculation shows. So that's one strong thing about independence. Independence means that typically that the probability of two events splits up as a product of two probabilities, but that's the same as checking if the joint density splits up as a product of two events. Limits. Okay, very good. So now let's just go back to our two examples. Let me just go back to this view and just go back and see if that's correct. Go back. Let me make this smaller. Let me come down to this level right here. So independence. So let me go back to this example that I had before. So suppose I look at the example that I had 5.4.3 and 5.4.5. For example. So in 5.4.3, you can clearly see that there'll be independence. Let's just check that. Let's try and see if we can check that. Let's just try and see. Okay, let's try and see. Overview, make it bigger. So I want to check in this example if this is true, right? So let's just go back to this. Let's take a simple example. So let's take a simple example. Let's just say, I'll just continue again with. So let's say example 5.4.3 continued. Let's say continued. So let's say I take my d to be the interval, let's say 0, 1, cos 3, 5. That is the rectangle. And then here you can easily observe that it's a small simple exercise that that f of xy is actually equal to 1 over 2 when x and y are an interval, are in D, and 0 other. That's what the joint density, x and y are uniform. D means this. Now, one can easily check that f sub x of x is going to be equal to 1 if x is in 0, 1 and 0 otherwise. And f sub x of y, f sub y of y is going to be equal to, let me just move the cross a little bit. Y is 1 if y is in 3, 5 and 0 otherwise. So 1 half. You can check this. It's easy to check. Once you check this, then you observe also that f of x comma y will split up as the product of the two densities. This is an exercise you can check, and that will imply that x and y are indeed independent. That means if you, so what does this pictorially mean? So what did I start off with? I start off with a d. Right? D was 0, 1 on the x-axis, or the y-axis, on the x-axis, sorry, and 3, 5 on the x-axis. Sorry, I'm sorry about that. This is flumbling. So x was 0, 1 and y was 3, 5. So x was 0, 1 and y was 3, 5. Right? Was 0, 3 to 1, 3, and I had 1, 5 and 3, 5. And what did I do? I picked an x and a y uniformly, was a uniformly chosen point in the domain. So x and y was uniform in the domain. So what does this calculation tell you? This tells you that, oh no, but look at this. That means the chance of choosing x and y uniformly in D is the same as choosing x first, independent of y. So what is x doing? X is f sub x of x. If you observe a little bit, that's just uniform 0, 1. And y is just uniform 3, 5. So that's the first thing you observe, that in these two calculations that, let me write this down in green. So let's just observe here that x is just uniform 0, 1, and y, let's let y in y is green, okay? Y is also uniform, but in interval 3, 5. That's just the difference. So that means choosing a point uniformly in the rectangle 0, 1 cross 3, 5 is the same as what you do. You go first here to x-axis. You choose a point uniformly in the interval 0, 1. So x is uniform 0, 1. And then you go in independent manner, you go and choose your point y in the interval 3, 5. So y is uniform 3, so 0, 1. Sorry about that. 0, 1. And y is uniform. Sorry, y is uniform. 3, 5. So that means if you do x and y independently, so this is independently, so it's independent. So you do this experiment independently. That's the same as choosing x and y uniform in D of rectangle. So that's what this means. That the x and the y are independent in that sense. So you can choose it independently, uniform in 3, 5, and 0, 1, and that's the same as choosing a point uniformly in the rectangle. But then it's sort of a rectangle is kind of crucial to this idea. So suppose I do the following. I do this next example. I'll do it next 5 minutes. Let's do the next example. I change the D. So let me continue the example. Suppose I change the D. I change D. Suppose we change D. This is always true. So this is always true. Always true. That is in the sense that if I pick a point in the square, is the same as changing as looking at x first and looking at y next, doing independence and choosing a point uniformly each. Let's just see. So the idea is here you take the D to be, let's say, the semicircle, let's say, right? So the semicircle would be maybe let's say D is equal to the set of all x comma y, for which x squared plus y squared is less than 20. So now I know that the area of the circle, semicircle, is going to be equal to just it's pi d, so it's like pi r squared, so just 25 times pi. That's the area of this the circle, right? Now your uniform x and y uniform in D would imply that f sub x comma y is equal to 1 over D, which is the area of D, which is 1 over 35 times pi, if x and y are in D and 0 otherwise. Now, so what is going on? What is going on? So now I have this circle. Let me write the circle down the bottom. So I have this circle and I'm choosing a point uniform, right? So I choose a point uniform. So x comma y is a point uniformly chosen on the circle. This is the origin. This radius is 5. So this is not a feature. Down blue. So this is the origin. This is my radius is 5. So x is uniform. X comma y is uniform. Now here is something that I will not do. It's a calculus exercise. It's a calculus exercise. One can check that if you do f sub x at x for a fixed point x, if you do, right? So x is somewhere fixed, you will have to integrate out y. So y is, you have to integrate out y in this region across from here to here on this line. So you can check that f sub x at x is just going to be equal to, I'll write this down, to be fxy dx dy, or dy, integrate out the y variable. Sorry about that. The y variable, right? But the y variable is only positive in the circle, so I have to just be careful. The same as going from, if you just think a little bit, it's just going from square root of 25 minus x squared to 25 plus x squared. Sorry, both are minus, plus minus. It's the negative square root to the positive square root of f at the point, now let's say x comma y dy. This happens if x is between minus 5 and 5 and 0 otherwise. Right? That just stems from this simple idea, right? So you have this thing here, the d here, you have this point x here, right? And then your y will only be, f is only positive in this region, right? So and these 2 points, this point is x comma y, and this point right here, y will go from this region. So this is the largest value y can take is this x comma square root of 25 minus x squared, and this lowest value is x comma minus 25. And this, if you work out as an exercise, you will get the same as you do the calculus, it will be 2 over 25 pi the square root of 25 minus x squared minus 5 is less than x is less than 1 and 0 otherwise. And you can do one trick, just show that you can use symmetry and show that even f sub y is the same thing. F sub y and y is the same as 2 over 25 pi square root of 25 minus y squared, then minus 5 is less than pi, less than y, and 0 otherwise. Once you do these 2 things, then this exercise is over, and you can easily observe that they are not independent. That is, choosing a point uniformly on the circle is not the same. So that this is not the same. This is not the same as choosing a point on x and y. So this implies that fx, let's say fxy at 0 is not the same. Fx0 is 2 over 25 pi. Fy at 0 is also 2 over 25 pi. And clearly, this is f sub xy. So f, the joint density at 0 comma 0 is 1 over 25 pi. And that's not the same as fx0 times fy. So they're not independent. So it's not. So x and y are not independent. So let me add it up here. So here we move this across. So here you say x and y are not independent. Excellent. Well done. So let me quickly recap the calculation. Let me do a split view. Let me do the same thing. So in the, come down here, and we come down here in the circle here. So when you had the rectangle, somehow you had independence, but when you had the circle, you lost the independence. because the regions did not sort of split up uniformly, sort of in a symmetric way in X and Y, and that's why you lost out on